Okay, so we are starting the session. This is the problem solving session for traffic engineering course for week 3. My name is Tanu Singh. I'm a PMRF scholar, Department of Civil Engineering, IIT Kanpur. So in this, first we will summarize all the lectures of the week 3. Then we will discuss some of the practice questions that will help you solve the assignment questions. And meanwhile, if you all have any doubts, you can let me know or enter on the chat box that we can discuss after summarizing the all the lectures. Okay, so we are starting with summarizing week 3 lectures. So in week 3, it has mainly focused on the shock waves in the traffic flow. So starting with the basic concepts of shock wave. So the traffic flow is mainly, as we have discussed in the previous week, is been described based on the three macroscopic parameters, that are speed, flow, and densities. So these parameters do not remain constant. They either change over a roadway or over a time. So these change due to the variations in the traffic demand, or due to change in the roadway geometry, or due to the traffic control conditions such as signals or signs. So any of the unique combination of the speed, flow, and density is referred to as a traffic state. Now, when a traffic moves from one state to another, for example, from free flow conditions to a congested, a boundary is formed between these two states. So this boundary separates two different traffic states in time-space domain, and this boundary is what we call as a shock wave. Therefore, shock wave represents a location where traffic conditions change abruptly over space and time. Before moving ahead, am I audible? So now moving ahead with the definitions. So shockwave represents the disk, as we have seen that the shockwave represents the difference change between two traffic states. So therefore we can say it represents the discontinuity in flow and density conditions. So since speed, flow, and density are interrelated, so we can say a change in flow and density automatically results in the change in speed as well. Hence, shock wave actually represents in the change in all traffic parameters. So based upon the movement, whether the shock wave is stationary, is moving, so we can divide into two types. First one is stationary. When the shock wave is fixed in a location, we called it as stationary shock wave, and if it changes position over time, then we name it as a moving shock wave. So for moving shock wave, the direction of movement is defined with respect to direction of traffic flow. If the shock wave moves in the same direction of traffic flow, it is called as forward moving. And if it moves in opposite direction of the traffic, it is called as backward moving shock wave. So now coming to the classification of the shock waves. So these first, we will go through the stationary shock wave. The stationary shock waves can further be classified into a frontal stationary shock wave or a rear stationary shock wave. A frontal stationary shock wave is located at the front downstream edge of the congested condition. On a congested condition, these typically occurs at locations such as stop lines, at signalized intersection, at bottlenecks, or lane drop conditions. Since its location is fixed, this shock wave does not move with respect to time. It is called as stationary. So whenever we stand at a traffic signal, so all the vehicles beyond before the traffic signals are all in the jam condition, and after the traffic signals there is, for example, there is no flow. So these are the two traffic states which is divided by a stationary shock wave. So this is an example of a stationary shock wave. The second type is the shock wave is the rear stationary shock wave. This is located at the rear end. In this condition, if the this failure occurs when the arrival flow rate is equals to the discharge flow rate. So in this, the Q neither continues or nor reduces. Therefore, it remains constant. If the number of vehicle arriving is equal to the number of vehicle moving out, so at the end of the compression condition, so in that it is called in this condition it is called as a rear stationary shock wave, though the as Q is not forming or reducing, so the shock wave is not moving, it remains constant, but it is termed as rear stationary shock wave. Then the other type was the moving shock wave. These shock waves propagate changes over time, either in forward or backward. Additionally, moving shock waves may be classified into the forming or recovery shock wave, depending upon whether the congestion is growing or dissipating. Now, the forming and recovery shock waves that are part of the moving shock waves. So, the forming shock waves occur when a new congested traffic state is developing and growing over time. In a forward forming shock wave, the shock waves moves in the direction of traffic flow and congestion spreads downstream. In the backward forming shock wave, the shock waves moves upstream opposite to the direction of the traffic flow. This indicates that the excess demand is being stored in the system and queues are propagating upstream. So these are two examples of forming shock waves. The one of the example of forming shock waves is if a truck enters into the road and all the vehicles moves with the speed of the truck, and no vehicles is able to overtake that truck, and all the vehicles has to go through the speed of the truck. So they reduces their speed, but the shock wave is moving forward. So that is an example of the forming shock wave. For the recovery, shock wave occurs when an existing congested traffic state is dissipating. Recovery means when there is a congested state, but now it is able to resolve. For example, if it is in the toll plaza condition, when there is a congested, but after the toll plaza thing, you can see a traffic state is being dissipating. So this is example of recovery shock wave. In forward recovery shock wave, the shock wave moves downstream, the Q length reduces from the rear. In backward recovery shock wave, the shock waves moves upstream and free flow or higher speed condition gradually replaces congested conditions. So these are the two types of the moving shock waves. Now, coming to the quantitative analysis of shock waves. So as we have seen that shock wave is a boundary condition of two different traffic states. So for example, first state is A, which has flow as QA, density as K, and speed as UA, whereas B is the another traffic state with flow QB, density KB, and speed UV. So this shock wave determined by omega AB determines the boundary movement. So the relative vehicle speed to shock, if there is a shock wave, there will be a relative vehicle speed. So in the upstream condition, for example, if it is UA minus omega AB, and downstream condition, it is UB minus omega B. So from the conservation of principle, so what happens? The number of vehicle crossing it from upstream must be equal to the number of vehicles leaving downstream. So because there will be no the number of vehicles that are for example, if the number of vehicles are coming in from this end, so the total number of vehicle moving out from this box or a boundary condition will be equal. So applying that principle, we get UA, that's speed into density, and here we can, as we said, is can be taken as a volume. Traffic volume is defined as the number of vehicles per unit time. So that is speed into density. So speed will be UA minus omega AB into KA, which is equals to UB minus omega AB into KB. So after solving this, what we get, omega AB is equals to QA minus QB upon KA minus KB. That is the formula for the shock wave speed. So the shock wave speed for the two traffic state, that is A and B, is defined as change in flow divided by change in the density. So mainly it is the slope of the line connecting A and B on the flow density curve. When we draw a flow density curve, so this was the flow density curve. So if, for example, A is this point and this was Q and this is density K. So the change traffic state from this point, we say B point is here and A point is somewhere here. So the slope of this line is termed as shock wave speed and it is calculated as change in QA. So whatever flow will be at QB, for example, this is QB and this is QA, divided by whatever is the density here at QB, which is being a difference of the density at QKA. So this is the interpreted as the speed of the shock wave. So shock waves depends upon flow and density differences. When we say there is a forward shock wave, that means QB is greater than QA and KB is also greater than KA. For example, the slope of this line where it is forward, because here QB is greater than QA and KB is also greater than KA. If B was somewhere here at this point, so in that condition, what was the condition? QB will be less than let me take a point. Okay. For example, another point is B is here. So now the slope will be somewhat like this. Then QB will be less than QA, which is given as an example of a backward shock wave where QB is less than KA, but KB, which will be here, will be greater than KA. So this will be the condition of backward shock wave. And there is a stationary. Stationary means when this straight line means both the Q and the density are equal. This is not example of stationary shock wave because density is different, but in the stationary condition, QB will be equals to QA and KB will be also equals to KA. So these are the three different conditions. Now coming to the example of signalized intersection. But before that, is anybody having any doubt till here? Okay, so there is no doubt. So we will understand the condition of signal. Okay, so just let me. Okay, so first I will explain with the example of the traffic signal. Okay, so as you can see from the screen, so okay, so we are taking a condition. For example, there is a road, so all the vehicles are moving with this with the speed that is with the free flow speed. So that condition we are taken as A when the vehicles are moving free flow speed. Then, for example, there comes a traffic signal which turns red. So whenever traffic signal turns red, all the vehicles, for example, are coming to this to the intersection at free flow condition, but when they reaches near the traffic signal, they are in traffic state B, which is in the stopped condition. And uh, beyond the traffic signal, what we see another traffic state which is C, where no flow is happening. Okay, and after that, if we see, then another we can say that way beyond the traffic signal, vehicles are moving again freely at free flow condition. Okay, so this is the condition number 2. The third condition is the traffic condition when another traffic signal turns green. So when it turns green, so the vehicles are coming to near the intersection at A as usual. Then the vehicle will, after it turns green, the vehicle will start moving with the full capacity, that is D, state D. So the vehicle will move from A to B, coming from A, then the vehicle which are in stopped position have been started to flow with their full capacity, that is D. So these are the three scenarios which happens in the traffic signal. So we can explain this using a flow versus density graph. Okay, so here we have drawn a flow versus density graph, which is in which is in this parabolic form, and we can say first was free flow condition. For example, we have taken a state A, that is was free flow condition somewhere here. We can take it anywhere that is before the capacity. We have taken it at this point, which is A. Then comes the condition B. B is the jam condition. Jam condition means when density is, when the flow is 0, but density is maximum. So B will be this condition. Okay. So we can say that B is this condition when the flow is 0 and density is maximum. Then comes the C condition. C condition is when the flow is also 0 and density is also 0. Okay. So this is C condition. And then comes the D condition when the flow is maximum, density is also optimum. Optimum conditions at the capacity, which is condition D. So these are the 4 different traffic state that happens when a traffic signal turns from at traffic intersection. So these are the 4 different traffic states. Therefore, we get different shock waves. Shock waves is when is the boundary between 2 traffic state. So what will be the different shock waves? So first shock wave will be connecting line A and B. So omega AB will be the first shock wave. Second shock wave will be omega BC. We can say we go from A to B, then from B to C. C will be another. Then there will be another condition of BD. This will be another. Whatever line connects these different traffic state is the speed of the shock wave. These all are the slope of these lines are termed as the speed of the shock waves. So we can also represent in the space versus time graph. So this is the space versus time graph, in which for example, this was the free flow condition where it was traffic state A. Then at time T naught, a traffic signal from T naught to T, for example, from T naught to T1, it turns red. So in red condition, what happens? We have to draw a straight. We have to draw a line. So in scenario this where the signal turns red, we get A to B and B to C. So A to B is this slope, right? So we will draw this slope from here point. We were drawing this slope, which is similar to AB here. We draw this slope A, B. So below that it will be A. And after this shock wave speed, the boundary condition, we get a state B. Okay, and then from between B and C, we get another state, another shock wave C. So for B to C, we see a straight line. So we draw a straight line from here to here, which is a red condition. And we say that below this, it is a B state. And after this line, we get a C state. Okay. So this we get for this is condition we get from T0 to T1 when the signal is red. So when signal turns green, it is A to B again. So A to B that continues. So A to B is another this. So we continue. So this was the slope from A to B. We continue this slope towards downward. And we another condition is from B to D. So this the slope of this line is this. This is more steeper than this one. So we get from this point, we draw another slope which is similar to this slope. You can see these two lines is represented as these two lines here. And we get below this line is state B and it is D and here it is A. So this is the area of the shock wave condition. Okay, so below is C. So these are the different slopes of the line, different shock wave conditions for traffic states A, B, C, and D. I hope it is cleared how the shock waves happens when it is traffic signal. Okay, so now coming to the, I hope it is clear given. Do you have any doubts regarding this shock wave and traffic signals? Then let me know. Else we will move to another example. Okay. So I'm taking now the another example, that is when a truck, that is a reduction in the capacity of road whenever a vehicle such as truck enters and there is no overtaking possibilities. The truck takes over all the space of the road and we cannot overtake the truck. So for that we have taken three different conditions. Okay, scenarios. Firstly, for example, all the vehicles are moving from the road at a free flow condition. So that is state A. Then a truck enters, for example, here is the intersection and truck enters the road. So what happens in this, and no vehicle can overtake this truck. Then all the vehicles that was coming to this road have to reduce their speed to make it equal to the speed of the truck. Okay. So this was condition A, where the vehicles were moving from coming to this road at free flow condition. Then all the vehicles that are just before the truck, they all reduce their speed from A to D. That is similar. That is equal to the speed of the truck. And then since there is no overtaking possibility, so there will be some road condition where that will be empty. So this empty road condition is represented by the condition C. Then comes the third scenario, where so the scenario 3 comes when a truck leaves the roadway. Okay, for example, a truck moves from this road to this and then it takes off ramp and moves on the road. So there then comes the condition D, when all the vehicles have accelerated and are moving with their full capacity. So that will be scenario D. So there is four different traffic state. First one was A, when vehicles were coming free flowing. Then comes the B condition, when all the vehicles, because they was not able to overtake the truck and truck has covered all the road condition. There comes the B state. Then comes the C state when the road is empty, as no vehicle are able to overtake. That is C condition. And then comes the D condition when all the vehicle will move with their free, with the speed, with the they will accelerate as truck off ramps the road, and they will move the road is using their full capacity. So these are the four different traffic states. So there, since there is different traffic states, so therefore we can see the shock wave speed, as shock waves is defined as the boundary between the different traffic states. So here we are representing these scenarios using the flow versus density graph, which is a parabolic. So we are assuming a traffic state A somewhere here, and then is the traffic state B, when all the vehicles are moving the speed of the truck. So it will come, so as we have seen, all the before this capacity or the optimum, this is the free flow condition, and after this optimum condition, this is the congested region. So since all the vehicles are moving with the truck or with the speed with their less of their capacity, so that will be coming in the congested condition. And since they are reducing their speed and there is no overtaking, so the flow on this road will be less than A, will be somewhat B. Okay, so we have drawn a B at point where the flow is less than A, as no vehicle can move. Okay, so this will be the B condition. Then comes the C when the road is empty. So this will be C when there is no flow and no density, C condition. And then is the D, the full capacity conditions. Okay, so these are the different traffic states. So all these lines that we connect with these different traffic states represent this speed of shock wave. So the speed of the shock wave is the slope of these lines, like omega AB, then BD, AD, and AC and BC. So but the slope of this line will be equal to the speed of the truck. Okay, because all the vehicles are moving at the speed, so the shock wave speed is equal to the speed of the truck. Okay, since the vehicle have transformed from A to B with to reduce it to the speed of the truck. Now we have represented this whole scenario in the space versus time graph also. So before that, all vehicles are moving, just a second, all vehicles are moving with the state A. Then comes a condition at this point. For example, truck enters somewhere here, this point, and leaves at this point. So this is the entry point of the truck, and this is the exit point of the truck. Okay, so before that, all were moving with condition A. Then this truck enters and all the vehicles have started, so they have reduced their speed. So we just replicate these condition over here. So from A to B, we see a slope which is similar. We replicate this slope over here from this point. So from A, this will be the AB shock wave speed. So below that it is the A, and above that it is B. Okay. Then at AB, and we also see in second scenario B to C condition. So we will also draw this slope, that is BC slope. We will replicate this slope over here. So it will be BC slope. Below that it is B, and above that it is C condition. Okay. So this is the scenario, second scenario. Then comes this third scenario. Okay. Third scenario, it is also A to B. So we continue this slope from A to B. It has been continued, and we also get B to D thing. Traffic state changes from B to D. So we see this. This is the slope, or we can say the speed of the shock wave between this traffic state B and D. So we replicate this slope over here, which is, as we can say, this is more steeper than this one. So we draw this, this over here. So we below that we get a traffic state B, and above that we get traffic state D. So we get these lines. The slope of these lines are represented as the slope of the shock wave speed. Okay. So again and then again, A to D will this here it will be A, then from A to D we get this slope. Between C and D also there is this slope. So we draw this slope over C to differentiate between condition C and D. So these are the different shock wave speeds. Okay. And also how to find this shock wave speeds. So to find these the shock wave speed, what we do, we have to just find the slope of this line. So we find the density at B. As if we know the flow at B, we can calculate flow at B, then density at B. Then we take this triangle and we get the slope of this line. Similarly, for this slope of this line, if we know the speed of truck, that will be equals to the speed of shock wave at for the condition omega AB. But if we don't know, we draw a paragram, and then we try to find the speed, the slope of this line. Similarly, we do for all these slopes of this line to get omega AB, omega BC, or omega DD. These are the speed of the shock wave speed. So these are the two examples. First one was the signalized intersection, and this one when there is the reduction in the capacity of the road. Now coming, I hope this is clear. Just so quantitatively, as we have seen, D at for the signalized interface, D was a zero flow downstream and B was the jam condition. That was, as you remember, that was the for the signal we have drawn something like this. So B was something. It was taking is saying B somewhere here and D somewhere here. Okay, but for example, in our example, D was here and C was here. Okay, so don't confuse. If here we have taken, we have renamed, for example. So it is B is here, D is here, and somewhat free flow condition A is here. Okay, so it says omega dB is 0. Why dB 0? Because the formula for omega BD will be QD minus QB upon KD minus KB. Okay, since Q, that is flow, is 0 for both the conditions, so it will be the shock wave speed will be 0. Then comes omega AD. Omega AD means slope of this line. Slope of this line is equals to the free flow speed because it is straight line. And as we all know, the slope of this Q versus K graph is equals to the free flow speed, that is UA. So it will be equals to UA. Then come omega AB. So omega AB means slope of the line connecting point A and B. So it will be equals to QA minus QB upon KA minus KB. For omega BC, it will be QC minus KJ minus KC. So QC, it has taken somewhere here. So QC, so it has taken here. C will be optimum. So QC minus Q, for example, here we should write QC minus QB, but B, for B the flow is 0. Okay, so this straight line where flow is 0. So it is not written, it is only written QC and divided by KJ minus KC because the density at point B is equals to jam condition. So it is, that's why it has written Kj, that is jam density minus Kc. So we get the different shock wave speed for different traffic state conditions. Okay. And if we need to find the maximum Q length, so maximum Q length will be omega AB into red time. Distance is equals to speed into time. The speed is the shock wave speed and time is the red time. So from this formula, you get the Q length for the traffic signal. And this was for the second example, that was for a slow moving vehicle when it creates platoons behind them. So platoons forming shock wave, backward moving from slow vehicles and forward moving. So when the vehicle enters, when it has entered for a particular duration, then it is backward moving shock wave. And when the truck moves away from the road, then what happens? All the vehicles are moving from B to D condition. That was, or moving from another shock waves happen, that is known as platoon dissipating shock waves or forward moving shock waves when the vehicle leaves. So these are the two phenomena that occurs. The maximum platoon length depends upon speed difference between Q truck and Q shock wave, density of traffic behind shock wave, that is KB, and shock wave speed formula. Okay. So then comes the, okay, so we have already discussed the shock wave at signalized under red forms. So at red signal, Q forms backward shock waves, moves upward. When it turns green signal, Q dissipates forward. Shock waves moves down straight. These are different formulas that are used to formulate the shock wave speed, as we have already discussed. And the Q length depends upon the duration of length and the shock wave speed that I had already defined. Q length is equals to red time and the shock wave speed. Till here, is anybody having problem with the shock wave? Everybody is able to understand what is shock wave and how it is solved. Whatever is the condition in the roadway, you have to draw. Okay, doubt on the shock wave speed. Okay, so shock wave speed, as we have discussed, shock wave speed is defined by the formula. Okay, so I'll just share this.
Madam.
Yes.
Madam, you told us shock wave speed is equal to Q upstream minus Q upstream. K upstream minus K upstream. How? Okay,
That, okay, so shock wave speed will be always equals to if there's two traffic straight. Just I'll just show you that. Okay, so as we have seen that the speed of shockwave will be, wait just a second. If there is two traffic condition, that is KA and Q. If there is two traffic conditions, for example, traffic state A and B, so shockwave speed will be always equals to QA minus QB or KA minus KB divided by KA. So this is the formula. If there is two traffic state, that is A and B. So shockwave speed will be the difference between their flow divided by difference between their density. And depending upon whether the flow is greater at B or it is less than, we define as three different conditions, that is forward, backward, or stationary. So this was all about the two conditions. Then comes the green shield model, green shield linear speed density relationship. We have already seen the green shield formula, that is U is equals to UF 1 minus K upon Kg. So shockwave speed for two traffic state, it has taken two traffic state, for example, X1 and X2, which is equals to K upon Kj, where K is some intensity for the state K X2. Then omega will be equals to UF 1 minus X1 minus X2. We put the formula here, then we will get the X1 minus X2. Okay. And if the small density discontinues, means if X1 is equals to X2, then 1 minus 2x1. Omega will be uf minus 2x1. Stopping, for the stopping condition, x2 is equals to 1 means k is equals to kj. In that, omega is equals to minus uf into x1. And if there is a starting q dissipation, means x1 is equals to 1, which will be equals to minus uf plus u2. Now coming to these application of shock waves. So shock waves has its application in the traffic management thing, where we can estimate platoon length behind, if any, for example, of the truck, if the truck enters the roadway, what will be the platoon length behind that slow moving vehicle. Then determination of the q length at signals, how much will be the q length, so that we can have a particular distance of the next signal or subsequent signals, what will be the next length, so that the q is not affected the another traffic signals. Then compute the time for platoon or q dissipation. Then predicting the use in the signal timings, like what will be the signal timings, because we have to see that the timing of one doesn't affect the other. Then the highway capacity and highway capacity planning, and also the incident management. If any incident happens, for example, if we have taken the example of the truck, instead of that, if some incident has happened, then in that condition also there will be no vehicle. We can see the empty road condition when some incident has happened, or for example, there is a snow in the road, or the road has been dismantled, and in that conditions, how to manage, how to dissipate the Q. As for that condition, we need the shockwave analysis. So the key principle is all calculation uses flow density relationship and the shockwave speed. The graph of flow density relationship is used to calculate the all the shockwave speed. Now, okay, so this. Now coming to the summary, a shockwave speed can be forward, backward, or stationary, depending upon traffic state, as we have already discussed. Then the quantitative analysis predicts the shockwave speed, what is the Q, platoon formation and dissipation times, then the maximum platoon Q length, and green shell model simplifies. Okay, so if there is no green shell model, we don't have the Q, the flow and density graph. With the help of that graph, we are able to get to do the analysis and find out the whatever is the shockwave speeds, Q length, or the delay time. Then essential tool for it is very essential tool for traffic engineers to manage congestion and optimize flow. If we know what will be the queue length or how much time will be required to dissipate the queue because of the bottleneck conditions, then we are able to optimize the flow. Okay, so these are the summaries of the or you can say takeaways from the shockwave scenarios. Now coming to the next part, that is traffic demand, volume, and capacity. So I hope the shock wave is clear to everyone, what it is, how it happens. Whenever the other questions comes in, how the shock wave speed is to be found, we are able to calculate it using different scenarios in the road. Like you can clearly draw stage 1, stage 2, stage 3. Try to plot it in the flow density graph, which will help you to find the slope of the line. Now, starting with the traffic demand, volume, and capacity. So, traffic volume we have already discussed is the number of vehicles. Okay. Okay, somebody have any doubt? Okay. Let me stop here. First, let's clear the doubt. No, a shock wave speed, it cannot be help in designing the width of the road, because width of the road depends upon the capacity. Mainly it depends upon the capacity. We do not decide the width of the road with the help of the shock wave. Shock wave analysis is mainly done to find the length of the queue, or how much time will it take it is not in terms of the width of the road. It is always in terms of the length. Though I understand it will depends upon if the width is more, the length will be less. But as a traffic engineer, we do not use shock wave analysis to decide the width of the roads, or we can uh, use it to find it. We can use to do the analysis for the shockwave thing, but we do not use vice versa, like using shockwave analysis, because shockwave happens once the road is already been designed on the road. Once the roadway is designed, everything is done, then we do the shockwave. So we do not use shockwave analysis to get the width of the road, of if we want to enhance the or extend the number of lanes, we do not use shockwave analysis. Okay, so anybody else is having any? Okay, if the road is recarpet or reconstructed, okay. So in that condition, we can use it, because then we can use it accordingly. If we see more for, but it is not, it is always the condition is happening, then the shockwave happens. No, shockwaves is depending upon the condition. First, it is signal condition. Okay. Second, if there is a slow moving, or there is a toll plaza, or if there are slow moving vehicles is ahead. So it is not a constant phenomena that is happening on the road daily. No, if there is, depending upon the signal, we can change the signal time, and we can use that efficiently. But we will since it is not a constant phenomena, we, depending upon shockwave, we do not change the width of the road or expand the number of lanes, because it is not a continuous phenomenon. It happens sometimes. It is not like every day, every time you will see the queue on the road. It's some condition. It's only in the peak hours you can see the queue length and the traffic signals, not whole of the day. So it's the shockwave analysis will not help to decide the width of the road or number of the lanes. It is only some situations where we see the change in the traffic state, so we do the analysis, but it's not the constant phenomena, or depending upon which. But if we will see the next thing, if the demand is more than the traffic volume, traffic capacity of the road, then we do it. Okay. Okay. So the first we start with the defining all the three terms, that is traffic demand, volume, and capacity. So traffic demand is the number of vehicles that want to pass a certain point in a hour. Okay. This we have already discussed. Okay. Then the observed volume is what actually passes through the road. Sometimes not everyone wants to go to, can actually do so. Okay. Third is the capacity. The capacity is finally the maximum number of vehicles a road can accommodate under stable conditions. Okay. So it is a road physical limit. So this is the demand that the people desire or wants to do. Okay, so that is demand. Volume is what actually we can see on the road, and capacity is the limit of the road, that road can accommodate these number of the vehicles together. Okay, so these are the three different terms. Now, the if the demand is less than or equal to capacity, okay, if we are demanding less than capacity, then it will be no congestion. But if the demand is more than the capacity, okay, then there will be the congestion if an queue occurs. But it is important to remember that just measuring traffic on congested road doesn't tell the whole story. The true demand may include drivers who take alternative roads, travel at different times, or even cancel trips. Okay, so demand vehicles are actual on the road that we see, but demand is we want to go to that road, but since we know that there will be congestion or something will happen, we change our route. So we want to use that road, but we are not going. So we all include that on the traffic demand. So if demand is more than the capacity, then congestion and queue occurs. If demand is less than the capacity, then no congestion occurs. Now, so the true demand. So in demand, true demand includes vehicle diverted to alternative route, vehicle traveling at different times, and trip cancelled due to congestion. So these are the different things that we include when we calculate the true demand of the route. Okay. Now coming to the queue thing. Okay, so queue formation and how queue dissipates. So queue forms when arrival rate exceeds the road capacity. When the number of vehicles arriving on the road is more than the capacity of the road. These mainly happens on ramps, off ramps, or merging point at intersection. When the number of vehicles arriving to the road is more than the capacity, then queue dissipation happens once the queue is formed. Okay, then when vehicle discharges at a rate usually slightly lower than the capacity, this is queue discharge rate. Okay, when rate of depreciation is equals to capacity minus actual. But we see the observed flow during congestion is equals to the capacity. So Q dissipates when capacity exceeds the arrival rate. Essentially, the road now clears the backlogs of the vehicles. Okay, so this is the whole thing. Q forms when the, for example, it's the road when number of arrival rate is more than the capacity of the road, then Q forms. And when these Q dissipate, we know this phenomena as the Q dissipation. Okay, and it only exceeds when capacity. Essentially, when the road, when this happens, the scenario when the road is clearing its backlog vehicles. Now coming to the bottleneck conditions. So bottleneck condition is a section of road when demand exceeds the capacity. Similarly, bottleneck is condition when the demand is greater than capacity. We say that the road is being bottlenecked. Then a hidden bottleneck is a condition in a downstream section that may appear uncongested because upstream bottleneck limits the traffic reaching it. Okay, you won't notice the congestion until the upstream problem is solved. Okay, so for example, here is the condition when the downstream because of some phenomena having here, we see here there is a condition of uncongested condition. Here the vehicles are moving clearly, but here think of something has happened and road is closed. So from 3 lane it has reduced to 2 lane. Okay, so what happens in downstream section appears uncongested due to upstream bottleneck. It only revealed when upstream bottleneck is removed. Okay, so this so here what happens, the road is not able to fully be used to its capacity because of some bottleneck conditions. Okay, so this phenomenon is known as hidden bottleneck condition. Then comes the demand starvation, when true demand cannot reach downstream section because the upstream bottlenecks restricts the flow. Okay, so this hidden bottleneck leads to the demand starvation. That is this here the true demand cannot reach the section due to some constraint that is happening in here. So upgrading one bottleneck may shift to the congestion downstream. Then, so in traffic planning, simply improving one bottleneck may shift congestion to another section. Comprehensive analysis is required to identify potential points. Okay, so if, for example, if we remove the bottleneck from here, if we remove and clear this road, then what we will see, when we'll see here, this road condition is now being congested, because initially it was free, but as we clear this bottleneck, it has been reduced to the condition where this condition is being congested. So we have to identify all potential bottlenecks before implementing capacity improvements. Okay. So capacity improvements here means the thing you were saying, that maybe some bottleneck condition that is being permanently here is not able to fully use its full capacity. Okay, so first we will not just improve the capacity of the road. We have to check all the bottleneck condition throughout the road before planning the new improvements. Then coming to capacity versus Q discharge. So capacity is the maximum flow the road can handle in stable condition. However, after congestion occurs, vehicle discharge at a slower rate. This is known as Q discharge rate. Okay. For example, here, take an example of intersection when a signal is red. When a signal is red, then vehicles are in jam condition, and here there is the empty road. Okay, so when after congestion, when vehicles start to discharge, so they discharge, so they take some time to realize, and the discharge is at lower rate of the capacity. So that Q discharge rate is always less than the capacity. Okay, so that is called as Q discharge rate, which is always less than the capacity of the road. Then coming to the impact of the traffic, if lower discharge rate means lower discharge rate means Q percent. If the rate at which the Q is moving forward is less, that means longer queues and delayed in clearing. Queue length and dissipation depends upon both access demand and discharge rate. Okay, so these are the impact on the traffic. Now, for traffic management and planning, we need to count for both demand and capacity balance and the dynamic of queue formation and dissipation. We just can't just do the balancing of demand and capacity. We need to find where the problem is, where if we need to remove the bottleneck, if we need to improve the dissipation rate, or whatever the condition is before analyzing different planning implication things. Therefore, understanding both capacity and discharge, the capacity of the road and the discharge is crucial for designing roads and controlling traffic effectively. Now coming to deterministic analysis. So in this type of analysis, we assume everything is predictable. The arrival, the departure, the traffic itself. Now in the first case, we focus on the variable service rate. That means the demand or the arrival rate of vehicles stay constant. Okay. And in but in the subsequent, we will see the variable thing. So here the demand is assumed to be constant and rate is maybe changes over the time. Now Q forms when demand exceeds. We have already discussed that whenever the demand is more than the capacity or the service rate, then there will be the Q. Okay, service rate comes it comes in the picture when we talk about the infrastructure such as toll plaza. So in toll plaza, Q depends upon the service rate of the toll plaza. Okay, so that's why it is said here as Q forms when demand exceeds the service rate. So the Q so the main outcome that we need to find is the maximum queue length, the average queue length, how long the queue lasts, the total delay experienced by the vehicles, and so this deterministic analysis is particularly useful when traffic disruptions are predictable. For example, planned maintenance on highway. Whenever this is deterministic, analysis is possible only when there is planned. For example, there is maintenance or there is toll plaza. So there we can do the deterministic. In deterministic means that the demand is constant, but the service rate we have assumed it to be changing. Then coming to the varying demand. So in the case where here we are saying that the service rate is constant, but demand varies over the time. So queues forms when demand temporarily exceeds the available capacity, and they dissipate when demand drops below it. Using deterministic analysis, we can calculate duration of the queue, maximum queue length, the number of affected vehicles, what is the average delay. So typically we assume that demand changes in a linear stepwise fashion to make calculation manageable. So these are the different ways where we assume, like first we assume a demand to be constant or service rates to be. This is just done to calculate what will be the different queuing thing, what will be the queue length, what will be the number of vehicles affected, or what will be the deal happening. So these are mainly done. These analysis are being done to find what will, if there's special events happening or there's traffic fluctuation in the traffic patterns, to do the analysis of these conditions. Now coming to the stochastic queuing analysis concept. Here both the arrival and service rate are random. These are not fixed. So queue depends upon the probability distribution. So here we assume different distribution to do the analysis. So, for example, arrival might follow a Poisson distribution, and service rate might follow an exponential distribution. Here we also consider factors like queue discipline, whether the vehicles. So since here everything is random, so we first fixed different things, like what will be the service discipline. It will be first in, first out, or last in, first out, or this priority based, if the queue length will be finite. So we will fix all the different parameters that we can fix or we know to do the stochastic queuing analysis. The number of channels, where there is single channel or multiple channel. For example, in case of toll booth, single channel in terms of the signalized intersection. Then what is the saturation condition? It is oversaturated or undersaturated. Oversaturated, the example of oversaturated, if there is a particular number of vehicles, if it remains only for the one cycle, it is then it is if it is more than one, it remains for the more than one traffic signal cycle, then we say it's oversaturated. And if it is less than one, it is very less than the one traffic signal timing, we say it's as the undersaturated queue. The other two queue situation, oversaturated and undersaturated. So the outcome in the stochastic analysis, like queue length, waiting time, total delay, are expected to be. So in since the arrival and service rate are random here, so the outcomes are also expressed as the probabilities or the expected values. So this approach is especially useful in the real world traffic where variability is high, such as at intersection, toll plaza, or parking lot. So the first study that we had discussed is mainly done where during for lane closure maintenance for signal phases, where we know we have stopped the vehicles for a particular, and we know the particular time till it has been stopped, or the particular signal cycle timing. But in these conditions, these are the real traffic conditions where the variability is high. We don't know that how much time will it take for a vehicle to get parked or toll booth. Okay, so now coming deterministic versus stochastic. So now after comparing with side-by-side interdeterministic analysis, arrival and service rate are fixed. Okay, that makes calculation straightforward and result predictable and suitable for control or predictable system. In stochastic analysis, both arrival and service rates are random. Results are probabilistic rather than exact, and this approach is more realistic for real-world situation. Both requires probability theory and understanding distribution. So, in short, we can say that deterministic is simple and predictable, whereas stochastic is complex but realistic. So the key parameters of consideration is that we, both that we can use both types of queuing analysis. First, we have the arrival rate, which could be constant or random. Then the service rate, which could be constant, random, or variable. Next is the queue discipline that can be for FIFO or last in first out, or it can be priority based that affects the waiting time. Then the queue length could be finite or infinite, determines the overflow or blocking impact. Then the duration of queue. Then the total delay is in the form of vehicle hours due to queuing. Then the number of vehicles that are being affected due to the queue. Then what is the channel layout? It's singular multiple service channel that also affects the processing time. Okay, so this was all about the third week lecture summary. I hope it's been cleared to everyone, or if anybody is having any doubt, they can let me know. We can have a discussion, or you can also write your questions in the chat box. Else, we can start with some of the practice questions. Okay.
Madam.
Yes.
Please give the explanation to the assignment questions, madam. During the class, they are seem to be very easy, but during the solving of the problems, some difficulties there, madam. Please.
Okay. Okay, we will today we will solve some of the numerical question. I hope that will help you to solve the week 3 assignment question. So we will do some of the practice questions that are numerical based things today. Okay. I hope that will. If you have any problem with specific question, you can let me know. We can discuss the previous week question today. We can do similarly with if the week 3 assignment that is been given, we can discuss some of the question next week in the week 4 if you have any doubt or you need explanation for any specific questions. But we can only discuss the week if the due date is over. Before the due date, I can't discuss that question. We can just practice some of the related question of that topic. Okay. So I'm starting with the first practice question. So first question is, which of the following statement is false? Total 4 shock waves are created during red time at signalized intersection. So is I'm audible to everyone? I hope I'm audible to you.
Yes, madam. Audible, madam.
Okay. Okay. So this is the first question. Which question is to find the statement which is false. So first is total 4 shocks are created during red time at signalized intersection. Then rear stationary shock wave is created when demand is equal to the flow in congested region. And then the backward forming shock wave is created upstream of stop line during red time at signalized intersection. And shock wave is defined as the boundary in time-space domain that demarcates a discontinuity in the flow density condition. I would request everyone to write their answers in the chat box. See what they propose. Okay. Clearly see it asks which of the statement is false. Okay, so first statement is total 4 shockwaves are created during red time at a signalized intersection. That is false statement. First, as we have seen that it was more than 4 shockwaves that was created. It was A to B, then B to C, then A to B, then so B to C, then C to D, and also from B to D, and also A to D. So there was more number of shockwaves that was created at signalized intersection. Now the second statement is rear stationary shock waves is created when demand is equal to the flow in congested region. That is false. In the rear stationary shock wave condition, what we have seen that the number of vehicles arriving is equals to number of vehicle dissipating at the rear end of the queue. So that is defined as the rear stationary shock wave. Then the third statement, backward forming shock wave is created upstream of uh, stop line during red time at its section. So that is correct because in the whenever there is a stop line at signalized intersection, we see the shock wave is the queue is forming before the stop line condition. All the vehicles arrive and they form the queue. So the shock wave condition is traveling backward. Okay, whenever the shock waves forms opposite to the direction of traffic flow, we say is a backward shock wave. So since the queue is forming back in the back direction of the stop line, so therefore we say backward forming shock wave is being created. The statement C is shock wave is defined as the boundary in the time-space domain that demands discontinue. This is true that because shock wave is defined as the boundary condition between state A and, for example, state A and state B, two different traffic state condition. So B, C, and D, all three are correct. The statement which is false is statement A. I hope it is clear to everyone. Okay. Now coming to the next question. So this is a numerical based question.
Madam, B false, madam, B. B is correct or false, madam? In first question, please.
Sorry for this is for the next two questions.
Madam, the first question, B is correct or false, madam?
So this is the data that is given. After that, I will show the two questions that is being given to solve depending upon this data. So there is a traffic volume at a section of two-lane undivided highway is 1500 vehicles per hour in each direction and density is about 25 vehicles per kilometer. A large dump truck loaded with soil from an adjacent construction site joins the traffic stream, travels at speed of 10 km for a length of 2.5 km along the upgrade before turning off onto a dump site. Due to relatively high flow in the other direction, it is impossible for any vehicles to pass the truck. Vehicle behind the truck are traveling at the speed of the truck, which result in formation of platoon of density of 100 vehicles per kilometer and flow rate is 1000 vehicles per kilometer per hour. So this is the data based upon which we have to solve two questions. First one is we have to find the speed of the shock wave that is generated because of entering of the truck into a traffic stream. And another is number of vehicles in the platoon by the time truck leaves the highway. So these are the two questions that needs to be found out. First, I will suggest you to draw uh, depending on the data given, draw a Q versus flow versus density graph. From there, it will be very clear to find the speed of the shock wave and also number of vehicles on the road. So this, I hope, see. I hope my screen is visible. So this was the speed versus flow diagram that flow versus density graph that we had discussed when we have seen that when a truck enters a road and what will be the different traffic conditions. So see this and try to find the solution of the answer. So you can see that the capacity is 1500 vehicles per hour and density is 25, but the speed of the truck that enters the road is 10 for 2.5 kilometer. And this is the two questions that needs to be done. So, uh, so I am waiting for doubt on shockwave speed. Okay. Okay, try to solve the condition. Okay. Try to solve it depending on two conditions. That is, shockwave has two formula is Q2 minus Q1 upon K2 minus K1. So Q2 is given as, for example, Q1 is given 1500, then Q2 is given as 1000. Here the density is given as 25, then density is given as 100. So two flow condition is given, two density is given, and just we have to keep them and get the shockwave speed. I'm waiting for 5 minutes for you all to solve it. After that, we can discuss the solution. But I would appreciate and encourage to first try.
Madam, my voice is audible or not, madam?
Hello?
Madam, my
Hello?
voice is audible. Audible, madam, my voice is.
Oh, uh, sorry, you're not audible to me.
Not audible, madam, my voice.
You can type your doubt. And also, if you are audible or not, if you could, so you're not audible, you can write your any of your doubt in the chat box as we can start solving the question. Okay. So, okay. So the first question was to find the speed of the shockwave. So the shockwave speed formula was change in flow divided by change in density. So change in flow is the two flow is given as 1500 and 1000. So change in flow divided by change in density. The density difference is 25 and 100. So these are the two conditions. First condition, when a vehicle, when the traffic state where the 1500 vehicle per hour was going with 25 kilometer density, but then it changed to 1000 and density is 100. So these two traffic state is given and we need to find the speed. We have to just put the value in the shockwave speed formula. And then we need to find what is the number of vehicles that are present in platoon. Okay, so let's start discussing the solution to the problem. Okay, so the first, I hope I'm audible and I'm discussing the solution to the first part. That is to find the speed of the shock wave. So for that, first the condition that is given is Q1 is equals to 1500, then Q2 is equals to 1000, K1 is 25, K2 is 100. The length of the till which the truck is there is 2.5 and the truck speed is 10. So the shockwave speed is given by Q2 minus K1 upon K2 minus K1, 1000 minus 1500 divided by 100 minus 25. So it will be minus 500 divided by 75, which will be equals to minus 6.67 kilometer per hour. So we have just put the values in the shockwave speed formula. So this is the first part where we have to find the speed of the shockwave. Now coming to the second part, which is to find the number of vehicles in the platoon. So for this, the time taken by a truck on the highway was 2.5, that was kilometer, and it was speed was 10, it was 0.25 hour. So the growth rate of platoon, the front of platoon moves with at a downstream at um, it was 10 kilometer per hour, but the rear of the platoon, that is shock waves, moves upstream at the speed of 6.67 kilometer per hour. Since both boundary moves away from each other, platoon length increases. So it is V growth is equals to Vf plus Vr. That will be 10 plus 6.67, which will be 16.67. So to platoon length when truck exists, it will be V growth into t. So length is equals to speed into time. Speed is the shockwave's total growth will be 16.67 into 0.25. The r for which the truck was there on the highway, it will be 4.17 kilometer. That is the platoon length. And if we need to find the number of vehicles, so it will be just density, that is in the second condition, into length. That is 100 into 4.17. So it will be around 416.7. With for the nearest integer, so it will be 417 vehicles. It didn't give it the total number of vehicles in the plateau. I hope it is clear.
Okay, madam. Clear, madam. Madam, clear.
Okay. Yeah, I hope it is clear. So now coming to the next question. So this is the next question data. That is, the demand is constant at 1100 vehicle per hour before the time 0 to 1 hour. Then it gradually increases from 1 to 1.5 hour. Then again constant at 1500 between 1.5 to 2.5, and then it gradually decreases between 2.5 to 3 hours, and again gradually decreases between 3.5 and 5 hours, and then remains constant at 900 vehicles per hour beyond 5 hours. Okay. So this is a question, and then we have to find difference. This was data, and then the questions that we need to answer is time when demand exceeds the capacity from start. Okay, so I will just draw the figure. Then time when demand rate decrease back to the capacity from start, and the size of the queue developing during the period when demand is greater than capacity. Okay, so first let's draw the figure for this. Okay, so let's draw it here. So what it says. So I will draw the demand with red. Okay. So first it's constant from 1100. Okay. So 1100 is constant from 0 to 1. Then it increases gradually and reaches, and again it reaches 1500, and then it constant from 1.5 to 2.5 hours. It's constant, and then again it decreases, and then it further again decreases to 900. So for example, it decreases from 15 to 1000. Okay. So let's draw it again. So first it is 1100, then it increases 1500, then it decreases to 1000, and then from here it again till 3.5, and then again it decreases, and from 5 it is 900. So here, but the capacity is 1300, which is somewhat here. Okay, so this is the capacity, which is 1300. Okay, so we need to find different condition. First is this x that we need to find. Okay, so first try to draw a graph depending upon the data, and then try to solve it. Okay, so just wait for around 2 minutes, around 5 minutes you all to solve, then we will discuss it. So now solving the question. So since here we need to find the question that was time in the okay. So first is to find demand when discussed. So there was this two. The first we draw the graph of the condition that is given. So it is given as firstly 1100 is constant demand, then it crosses to increases to 1500, then it's constant, then it further decreases to 1000, and then it further decreases to 900. So it is 900, it is 1100, and there comes that is 1000, and here it is 1500. So and the capacity is 1300. So firstly we need to find the value of x, and then this one. Okay. So how to find the value of x, since it is going from 1 point, it's in the question it is being given from 1 hour 1.5, and it is gradually increasing from 1500, from 1100 to 1500 in between, and it is being given as 0.5 hours. Solving it, we will get the value of x. Similarly, we need to find the value of y. So again, when we solve it, 1500 minus 1000 upon whatever is the duration that has been given here till here, and then what is the change that has been happening here. We just write the time difference between here. We'll get the value, we'll get some value, then we will add that value. So we got the value that we get from here is 0.4, and the value of x that we get is 1.25 hours after solution, and here we get it as 0.4. So the total y that we get is 2.5, because the time here is 2.5 and here it is 3. So 2.5 plus 0.4, so it comes out to be 2.9 hours. Okay, so these are the two values that we need to find. and then get the size of Q developing during the period when demand is greater than capacity. So the time that is more than the capacity will be from here we get the total value of x and value of y. Then after further solving to get the size of Q, so for the size of Q we need to find the area of in the capacity and demand curve. So we need to find the area here. So therefore here we divide it, we get the triangle that we get from here, then the rectangle that is here, and then again a small triangle. So the rectangle between 1.5 hours to 0.5 hours will be equals to half base 0.25 into height, that is 200, 1300 minus 1500, 200, so we get 25. Similarly, we get the rectangle that will be 1 times into 200, but 1 hour difference is there, 200, and in here from 2.5 hours to 2.9 hours we get half, base is 0.4 and height is 200, we get 40. The total Q size will be 25 plus 200 plus 40 will be equals to 265. So that's how we solve this question. Now coming to the another question, that is accept or reject. Traffic demand is equal to observed traffic volume in absence of congestion. So in the absence of congestion, when there is no congestion, there is no capacity constraint, so all demand trips can be served. So that means all observed traffic volume equals to the traffic demand. So therefore the answer to this question will be equals to A, that is acceptable. So the statement is correct. On the next question, that is demand starvation can cause hidden bottlenecks. So can demand starvation can cause hidden bottlenecks or not? So the statement here, if you accept this statement, so the reason behind is that the demand starvation mainly occurs when the roadway or link has very low traffic demand. Even if the roadway is capable of carrying more vehicles, insufficient demand prevents it from reaching its full utilization. Then coming to the hidden bottlenecks, a bottleneck is a location in the network that limits the flow. So a hidden bottleneck is one that exists but there is no obvious reason that the road never appears congested, because the road never appears congested. So how demand starvation cause hidden bottleneck? If a road could handle high volumes but experience low demand, congestion can so in this case congestion never occurs, so the bottleneck is not visible. Planners may underestimate the potential bottleneck because the road looks underutilized. Therefore the statement is correct. Now coming to the next question, that is accept or reject the statement length of the queue will less if the vehicle discharge rate compared to the discharge rate at capacity. The length of the queue will be less if vehicles discharge rate compared to discharge rate. So we are comparing two things here for this question. First is discharge rate at capacity and discharge rate below capacity. So discharge rate at capacity is maximum possible flow and discharge rate below capacity is slower than the capacity. So therefore if the discharge is less than the capacity, that means the queue grows faster when the demand is high because vehicle leaves more slowly than they could at capacity. Therefore, statement is rejected. Okay. one other way we can say that the slower discharge is equals to longer queues under the same demand. Only if demand is very low, queue may not form at all, but in general traffic theory, comparing at same arrival rate, lower discharge increases the queue length. Therefore, we reject this statement. This was all for this week's problem solving session. I hope there is no doubt. If you have any doubt, you can write in the chat box. We can discuss it. Okay. Since there is no doubt, so we are closing the session. We will meet again next week for the week 4 problem solving session. Thank you everyone.